Hello. In this second video on Gauss's law, I'm first going to quickly review what the law actually states. I am then going to give you a general method of applying Gauss's law to calculate the electric field for certain setups, for certain charge distributions with symmetries. And then I'm going to apply that to a bunch of examples. So here's what Gauss's law states, and we got there at the end of the first video, part 1 on Gauss's law. If you haven't watched that, you probably want to watch that first. So the law states that if you take the area integral, and this is the area, an integral over a surface, and that surface is closed, it means that you imagine some kind of three-dimensional surface. It has to be such that there is an inside and an outside. And if you were to fill the inside up with water, it wouldn't come out. That's kind of the idea. Right? There's an inside and outside, and there's no way to get from the inside to the outside. That's what we mean by a closed surface. Or we can think of it, if you want to visualize it, say you take a balloon and you fill it with air, and you close it with a knot. Now the air inside is going to stay inside, the air out is outside. You can squish the balloon into different shapes, but it's always going to be closed. Right? There's no way for the air inside to come out and vice versa. So that's what we mean by a closed surface. But remember, taking the integral means we're doing some kind of sum. We're summing up such that in the end we've summed up some quantity over all the different bits that make up that area. And the thing we're summing up is the electric flux. If you don't know what it is, again, go back to the first video where I explain this in detail. And Gauss's law states that this integral, the integral of the flux over any closed surface, you get to choose, that's equal to the charge that's inside divided by the epsilon zero constant, which is just a constant that determines the overall strength of electrostatic interactions. It's the constant of nature. Could argue it's to do with the units we choose and so on, but for our purposes it just determines the overall strength. It has a value that you can look up, and that's that. And the charge inside, well, that means in this case a charge inside the balloon, right, if you go with that analogy. It doesn't matter how you shape your balloon, something is either inside or outside, and we don't care about what's outside. Right? You can put 100 coulombs right next to the surface. If it's not inside, it doesn't matter. It doesn't count. If there's positive and negative, well, you just have positive. It's a total. So you get positive, 5 coulombs minus negative 4 coulombs. So you're going to end up with 1 coulomb. Right? It's really just the net total charge. If there's the same amount of positive and negative, well, then that's 0. All right. So let's apply this. Now let's see how this is useful to calculate the electric field in certain situations. So I'm going to give you the general rules to do this, right? And I've written them out already. And then we're going to apply them, and I think that'll actually help to make sense of what this is saying. So suppose your task is to find the electric field, and you're given some kind of setup of charges. So it could be there's a point charge here. It could be you've got a really long line of charges, like a long cable of charges. It could be that you've got a hollow sphere and the surface of the sphere is charged. It could be you could have a large sheet of charges, or maybe a large sheet that's positively charged and on top of it a large sheet that's negatively charged. Something like that, right? So you're given some kind of setup where in the past, meaning just last week, we would have had to do an integration to figure out what the electric field is. Gauss's law is going to allow us to avoid that integration, to not actually do it. We sort of let Gauss's law do the integration for us, and we don't actually have to evaluate any integral. So we're going to pick our surface, right? We're going to pick the surface. Remember, the law is applied to any imaginable surface, as long as it's closed. So we can pick whatever, but we want to pick one that is actually useful for our calculation. And the way we do this is as follows. I want to pick a surface that matches the symmetry of the charge distribution. What does that mean? That means if, say, we have a charge distribution that is symmetrical under rotation. So imagine if we put a long rod like this one here, like imagine this is an infinitely long rod. Then this pencil, I can rotate it like this. And if you imagine it were perfectly round, then this wouldn't change the setup in any way at all, right? So that means rotation like this is one of the symmetries of the setup. If this pencil were infinitely long, then moving it forwards and backwards would also not change anything. So that's also symmetry. If this, again, this pencil is imagine it's an infinitely long line, if I imagine flipping it, again, the new setup looks exactly like the older one. It's just a long line. So any sort of transformation you can do, transformation meaning you're rotating something, you're switching directions, you're moving something forwards or backwards, any transformation you can do that does not change what the actual setup looks like, that is a symmetry, right? If this is the setup and I rotated it, and your friend is late to lecture and walks into the room right now, well, they can't tell that I've rotated it already. And if I rotate again, well, again, there's no difference from before, right? That is what we mean by a symmetry. The second condition for our Gaussian surface to be useful is, well, we want the point where we want to find the electric field to be on the surface, right? So if we, and part of the difficulty is here is that you always have to visualize this in 3D. If you imagine this is my long stick of charge, you can imagine it's infinitely long, and I want to figure out what is the electric field right here at the tip of this pencil here. Well, then whatever surface I'm going to pick, what Gaussian surface, it should sort of go through the air somewhere around here, where that tip of the pencil, where I want to find the electric field, is touching the surface. We're going to see it in action. That'll hopefully make more sense. So that's going to be our first step, to figure out what Gaussian surface do we want to use that's useful. The second thing is then we're going to, well, sort of justify why this is the right choice. And we're justifying it based on those symmetry considerations. And the thing we want to justify is that the flux through that surface, through a small element of area on that surface, is the same everywhere. Right? So you want to pick a surface such that that thing you're integrating over, or that you're integrating, the integrand of Gauss' law, that is constant everywhere. Because if it's constant, then the integral will be trivially easy. So this is kind of where the power of Gauss' law comes in. That we get to pick any surface we want, so we pick one that makes our integral super easy by making the thing inside the integral constant. And you get that exactly when you pick the right symmetry that matches the symmetry of your setup. Again, this sounds very abstract, but we're going to see it in action in a second. The third step is we're going to calculate what the flux is, right? So this is the flux. This is the left-hand side of Gauss' law. And now if you did everything right, that is super easy, because what you get is that this thing is constant, so the constant comes out, and you just integrate over the area, the little chunks of area. So you just add up all the different areas until you've covered the surface. So that means it's just this constant that comes out the front, and it's usually just the electric field, the magnitude of the electric field. And then you multiply just by the total area, because summing up the individual chunks of area until you've made the whole area, well, you're just going to get the total area. Again, this is a complicated way of saying something trivial. And that is exactly the power of Gauss' law, that we can make this complicated calculation trivially easy, as long as we understand what we're doing, right? So this is going to be a constant. Constant can go out in front of the integral. All that's left inside it is just the sum of the tiny area chunks. with each one absolute value of the area vector just being the actual, size of the area, how many square millimeters. So you calculate that, and that's going to be easy because you picked a nice surface in the first place. If you pick a bad surface, right, it doesn't match the symmetry, well, this is not constant, the integral is difficult, okay, well, you're not really getting anything out of using Gauss's law. If you pick the right surface, then this integral we have to evaluate really becomes super, super easy and just a constant times the area of our Gaussian surface. And we'll see that again, right? We'll see it in action. So we're almost there. So we've calculated the left-hand side of Gauss's law. What about the right-hand side? Well, this is usually easier. We just figure out what is the total charge inside our surface. That depends on how you pick your surface. How long is it? How big is it? Is a certain charge that's sitting somewhere inside or outside? But usually it's something you can determine fairly straightforwardly just by looking at the setup. And again, we'll see it happen. And finally, we just solve. We solve Gauss's law. We equate the left side, right-hand side, and we solve for the unknown electric field. So here's some examples we're going to go through. I want to go through the example I'm going to pick is a sphere of radius r. So a sphere like is a hollow ball, right? All the charges on the surface, total charge q. It's a little bit, it's not a point charge, but from far away it might look like a point charge because it's a small ball. Then I want to look at a long rod, the example I've given with the pencil, of charge density lambda. This is a linear charge density, meaning charge per length, right? How many coulombs per meter? I tell you that, and you can tell me what's the electric field a certain distance away from the rod. We're going to look at a sheet of charge density eta, and that's charge per area, right? So imagine this piece of paper being the sheet. You can imagine there's charge sort of spread out all over roughly equally. Each square centimeter has a certain number of coulombs in it. And then there are two more examples, I think, that are, these are just a few, there are lots more examples, although those cover the main symmetries you're going to encounter. We're talking about the gravitational field inside the Earth. Now, we could do an analogous calculation for a ball of charge where the charge is spread out not over the surface, but over the whole volume. But I want to do a gravitational field instead to just show you that analogy between Newton's law of gravity and electrostatics. Like Newton's theory of gravity looks very, very similar to electrostatics, and so it has its own Gauss's law. It's just you probably didn't meet it when you looked at Newton's theory of gravity in Physics 161 or whatever equivalent course you took. And then the final little challenge problem is, well, it's gonna be fun. You'll see. All right, well, let's get started. Let's apply those steps. So example 1. Example 1 is a spherical shell. When you say a spherical shell, right, we mean a sphere where the inside is empty. So all the charge is on the surface. Now I want to draw it in 3D. I'm bad at drawing stuff in 3D. So I'm just going to draw it like this, right? Imagine this is a ball, not just a circle. And we're going to pretend all the charge is on the surface. And it's equally spread out across the whole surface. So one thing you could calculate is how much charge is there per, square millimeter. In that case, you just take Q and divide it by the total surface of the sphere. If the sphere has a radius r, it's going to be 4 pi r squared. But we're actually not going to need to do that. So I want to figure out what is the electric field at distance r. So I'm using little r to mean the distance from the center where I want to find the electric field, and big R to be the fixed radius of the sphere. The distance r from the center. So we're trying to figure out. Now, the first thing we look at is the symmetry. So we're saying, okay, this is a sphere. So if you imagine you have a sphere, you can rotate it in any direction and it's still the same sphere. Right? Imagine a perfectly smooth ball you hold in your hands, you can't tell which side you're looking at. Right? There's no sort of front and back, it's all the same. So you can rotate it like, you can spin it like this, you can spin it like this, you can spin it like this. It doesn't change anything. So that implies that the electric field is also going to be spherically symmetric. So let's write this down. We observe that the setup, the charge distribution, is spherically symmetric. And therefore the electric field is spherically symmetric. Right? If I can't tell which side is front, which side is back, well, I shouldn't be able to tell with the electric field either, because there's nothing causing the electric field in the front to be different from the electric field on the back, or the electric field over here be different from the electric field over here. It's all the same. It looks the same from all directions. So that means our Gaussian surface is going to be a sphere centered at the same point. Should probably draw where r is, right? It could be any r. I'm going to draw it out here, right? Some distance r. But we're also going to think about what happens if r is less than the radius, right? If the point here is inside the sphere. Think about that too. So the electric field is spherically symmetric, and let's assume our charge is positive, then we know that the electric field must be pointing just outwards from the surface. The electric field is spherically symmetric, so we pick our S, our Gaussian surface, to be a sphere. So let me draw this again. So here's my center. Here's my sphere of radius r. I want to find the electric field here. I know that the electric field is going to be pointing radially inwards or outwards. Right? Okay. How do I know that the electric field is going to be pointing either this way or the other way? I know that because if it were pointing to one side at some angle, then this would violate the symmetry of the setup, right? There's no reason the electric field could be pointing this way rather than this way, right? It has to be pointing like this, because if it were pointing like this, then it would be like a preferred direction around the sphere. It would break the symmetry. Like, how would the field know whether it should be pointing this way or that way? Or more technically, imagine the field was pointing, I'm going to draw this in very faint pencil, imagine the field was pointing this way here, right? Then imagine I spin my sphere around this axis here. So I'm going to flip it. Well then, the electric field will be pointing this way, right? Because I've just spun my whole setup. But that's bizarre, because I haven't changed the distribution at all, because by rotating a sphere doesn't change the sphere. It doesn't change where the charges are. So that's a contradiction, right? Therefore, I know that the electric field has to be radially, And if it's a positive charge, then I can, make an informed guess it's going to be outwards. Let's pick our surface S. I want our surface S to match the symmetry, so it's going to be a sphere. And I want it to go through this point here. So we're going to pick our surface S to be a slightly bigger sphere of, in this case radius r. Right, so we choose our sphere to be our imagined Gaussian surface. Right, this is something, a mathematical thing we come up with. Right? What's physically there is the solid sphere of radius capital R. We're going to imagine this sphere here because this sphere includes our point and because it matches the symmetry of our setup. So that was, in a sense, step 1, if you go back in the video or if you go back in any notes you took. So now we're going to just justify, well, is the flux the same? That is the same is obvious now because I could have like drawn this instead up here, instead of down here, right? This point here, and everything would look the same, right? No matter where you are, for a given distance from the center, the sphere looks the same no matter what point you're at. So if I now look at some small area element, you have to remember this is 3D, right? This is a sphere, not just like a circle inside another circle. It's a sort of two spheres centered at the same point, one bigger than the other. If I look at some small sort of area element here, right, then the flag that determines direction of my area element sticks out like this, and the electric field sticks out in the same direction. I don't know what the magnitude is, right, but I know the direction. So those two together imply that E dot dA, the flux through this tiny little window, right? How many electric field lines are going through the window? That is equal to the strength of the E field at the distance r. I'm just going to write ER without the arrow, meaning this is just the magnitude of it, times dA. But again, I could write the magnitude of the vector dA, but I'm just going to write dA without the arrow to mean, look, this is just the actual size, how many square millimeter, what is this tiny little area here. Now for the flux, I'd also need times the cosine of the angle between them, right? Again, if you don't remember that, look back at part 1 video, the first video on Gauss's law. But because they're pointing in the same direction, the angle is 0. And if this one is 0, that means this thing is just 1, so I can ignore it. Okay, now this was step 2, because this same principle applies to any part of the surface, right? I could have written down exactly the same thing here and here and here and here. In all parts, the electric field strength is the same because of that symmetry argument. Because if it wasn't, like it was stronger here than here, then somehow this side would be different from that side, but that contradicts the fact that the sphere looks the same from all directions. So now let's move on to step 3. Before we go to step 3, though, we should possibly just annotate what we're doing here. So this part, I guess, you would count as steps 1 and 2. Right, picking our surface and justifying why it is the right choice, why it makes our flux through each individual little window the same. And in this case makes it easy that the angle is also just 0, which you're going to find more often than not actually to be the case. So step 3 is then to calculate the actual flux through the whole surface, right? So step 3, so we're going to do phi, the flux, the electric flux, is the integral over our surface S. I guess I should keep this color coded, right? That's the green one. Our big sphere of radius little r. And we're integrating over the flux through each individual one. So this means we're summing up, right? We're summing up until we've covered the whole area, the flux for each individual tiny chunk of area. But now we know that this thing here is the same for each individual chunk. So I can just write this. I can take the E as a function of radius, right? It's not the same everywhere, but it's the same everywhere as long as we are on a sphere, on a shell of the same radius, times the integral over, so the sum over just the little area, how big is the area. But this integral here, right, that is just the total area of our big sphere. Right? So this is because the sphere we picked is a sphere of radius little r. This is going to come to the area of our surface, which is 4 pi r squared. Because that is you could say this is the equation that gives me the area of a sphere, but you can also work this out if you know about multivariable integration in polar coordinates. Okay, area of the sphere times, right, whatever the value of the field is, radius r. We don't know that. That's the thing we're trying to find. Right, so now we've evaluated the integral. There's one unknown, the electric field, but we figure out the left-hand side of Gauss's law. Okay. So now we come to step 4, which is the right-hand side of Gauss's law. So let me continue here. Adjust the camera a little bit. So step 4. That is finding the charge inside our surface. Right? So what is the total charge inside? Q inside, what's it equal? Well, let's look at the picture. This is our big ball. This is our little ball. All the charge, setup told us, is on the surface of this sphere. So all of it is inside that big ball here. So that's just the whole Q. Right? So in this case, all of it because the whole of the charged sphere is inside our Gaussian surface, our imagined sphere. So what does that imply? Well, that implies that for ER, the electric field, strength, distance r from the center, times 4 pi r squared, little r. So the distance to our point where we want to find the electric field is Q, which is the total charge of the sphere, divided by epsilon 0. Now, just to clarify, this Q here, right, we were told there's a total charge Q here. So this could have said the total charge of 5 coulombs on the surface, and then this Q here would be, I would have put in 5 coulombs, right? The Q inside is just, this is a sort of symbolic, I guess, symbol we're going to use just to mean, well, what is the total charge inside? So this, the total charge inside here, has the value, could be 5 coulombs, but we're just going to call it big Q. Okay, so what does that mean? Well, we're given Q, right, given it symbolically, but we could have been told 5 coulombs or whatever. R is something, you know, maybe we chose, or we were asked to find it at a specific distance, or maybe we just asked to find it, the electric field strength, for any distance r from the center. But then we just do step 5, right? This was step 4. Guess I should change color just to visually distinguish it. Right, step 5, super easy. Just going to rearrange this, and we find that ER is equal to, so the electric field strength, the distance r from the center, is Q over 4 pi, by taking this down here, epsilon naught r squared, which you might recognize, right? This is Coulomb's law. Except we know Coulomb's law holds for a point charge. Well, if this had been a point charge, or the Q in the center, you know, we would have done the same thing, or everything would have worked out the same. So what we've proved here, if you like, is that Coulomb's law, Q over 4 pi epsilon naught r squared, right, this thing here, 1 over 4 pi epsilon naught, that is K, the electric constant. What we've proved is that this expression doesn't only hold for a point charge, but also for a spherical shell, as long as you're outside it. You want to know the electric field outside it. You could have easily proved the same thing for a solid ball of charge, or for a shell and then another charge on the inside, or anything that's spherically symmetric. As long as you're outside of it all, right, all the charge is inside, the symmetry is spherical, all the calculation goes through the same, you're going to end up with Coulomb's law. And now, if you remember that Gauss's law also exists for gravity, and I haven't shown that to you yet, but I just stated it, we're going to see it, but let's just accept it as a fact. Now we've proved that, or could have done an equivalent proof for gravity, that you should measure the distance, say between two objects, to calculate a gravitational pull from the center, right? So we calculate my weight on Earth using Newton's law of gravity. I'm going to use the distance between myself and the center of the Earth. I pretend all the mass is in the center, and that's okay, because, as we've shown here for electric fields, right, that as long as you're outside the sphere, the law is exactly the same as if all the charge had been in the center. Actually, we're going to come back to the gravitational field for the Earth later on. But this is our final answer. Okay. There are a couple more examples to do. This was our first one. I'm going to stop this video here, and I'm going to do the other examples in part 3 to stop this very video from becoming too long. See you in part 3.